Hello everyone. So in this video, we are going to see the oscillating neutral phenomena in case of star-star connection. So to understand this oscillating neutral phenomena, first of all, you must know the exciting phenomena in case of transformer. So this oscillating neutral comes into picture because of non-linearity in magnetic BH curve. So let me explain it first. Let's say I'm considering a non-linear BH curve because transformer has a core ferromagnetic material. It has a BH curve. Like so, for simplicity, I am considering only non-linear BH curve, and it has no hysteresis. For example, it's for some up to some current it is linear, but after that it will be like somewhat non-linear in nature. So it is a non-linear BH curve. I have this kind of BH curve of a transformer core material. uh, so this non-linear BH curve which is basically responsible to produce such kind of oscillating neutral phenomena. So these are my neutral point. This is my neutral point. Okay. In case of oscillating neutral, the phase voltages, actually the phase voltage magnitude varies time to time. Okay, we will see how the magnitude of the phase voltage get changes. Let's say you have the nonlinear BH curve, and in case of nonlinear BH curve, and B is proportional to flux, and H is proportional to current. Okay, because of nonlinearity in the BH curve, if my uh, current is current is sinusoids, current is sinusoidal in nature, my flux will not be sinusoids. Okay, and if my flux is sinusoid, my current will not be pure sine wave. It will contain some harmonic. Like if any of the quantity is in sinusoidal in nature, the other one will not be sinusoids because of the nonlinear BH curve. You can also say like that, think like that way. Like let's say you have a flux density waveform, flux waveform. Let's say this is your flux waveform. So till this point, you will get the current. It will follow the same kind of relationship. Like in case of linearity, we can say the y equals to mx formula we can apply. Like if my x is sinusoids in nature, it is, let's say x is some kind of sinusoid. Let's say x is equal to some xm sine omega t. Then my y will also be m xm sine omega t, like that. But my linearity, this y equal to mx formula is valid till this point. After that, there is non-linearity. So you cannot even apply this y equal to mx formula. So if any of the quantity is sinusoidal in nature, the other quantity will not be purely sinusoids. So if my flux waveform, say let's say it is my flux waveform, which is in sinusoidal in nature, in case of nonlinear BH curve, the current, or we can say this is my exciting current that is responsible to set up the flux in the core. It is my exciting current. This exciting current will not be sinusoidal, purely sine wave. It will be peaky in nature. So it will be something like that. It will be peaky. It is peaky because of nonlinear BH curve, and something in this side also it will happen. Let's say maybe roughly if I try to draw, it will be peaky in nature. So if my flux is sinusoid, my exciting current will be peaky in nature. And for example, if I consider my exciting current is sinusoidal in nature, let's say my exciting current is sinusoidal in nature. Let's say it is my B. This is my non-linear BH curve, and my H is proportional to exciting current and B is proportional to phi. Okay. Now, let's say my exciting current is sinusoidal in purely sine wave. Exciting current is purely sine wave. In that case, my flux will be flat topped in nature, because till this point, it will follow the same nature. But after that, my flux relation between flux and exciting current will not be y equal to mx kind of relationship. So it will be flat topped in nature, and maybe till this point it will rise sinusoids, and after that point it will be like somewhat flat topped in nature, right? So this is the two fundamental things that you must know. Okay, now we'll see one more thing, one more fundamental we'll try to see. Now you can you can check this particular exciting current waveform. This the nature of the exciting current, it is, if you think from signal point of view, it is the signal is odd in nature. The signal is odd in nature, and this signal contain odd half wave symmetry. So that means it will contain only odd harmonics in that. So if I write the expression of the exciting current, maybe it has some fundamental quantity sine omega 1 t. It will have third harmonic component sine 3 omega t, I 3 5 sine 5 omega t. Okay, so those odd harmonics will come in exciting current of the transformer because of the nonlinear BH curve. For simplification, I am just considering fundamental quantity and the third harmonic quantity. I'm not going to the fifth, seventh, and all of this harmonic quantity. So let's erase these things. Now, tell me one thing. This third harmonic component, if you see from for the three phases, let's say it was for phase number one, IEA of t. So IEA1 sine omega 1 t plus IEA3 sine 3 omega t, omega 1 t, let's say this is the omega 1. And if you see for phase B, the exciting current IEB of t, IEA1 sine omega 1 t, there will be 120-degree time displacement plus IEA3 sine 3 omega 1 t minus 120-degree. IEC C phase, for C phase it will be IEA1 sine omega 1 t plus 120-degree plus IEA3 sine 3 omega 1 t plus 120-degree. If you see the third harmonic components across three phases, they are all in the same phase, because if you expand this particular quantity sine 3 omega 1 t minus 120-degree, it is nothing but sine 3 omega 1 t minus 360-degree. So it is sine 3 omega t only. And same for the C phase also. So third harmonic quantity that are present in the exciting current, all are in the same phase. Now tell me one thing, if all are in the same phase, then let's say my neutral of the primary side of this extra connection is not grounded. So if third harmonic current is coming from all the three phases, third harmonic current, and third harmonic current, they are coming, and at the neutral point there is no another path to flow the third harmonic component, because all are in the same phase. So if they come here, and since all are in the same phase, the summation is not basically there, the summation of these three currents are not zero. That means third harmonic current cannot flow through the line or even phase also. Like if your neutral is not grounded, then there is no return path for the flow of third harmonic current. But for example, if there is a my neutral is grounded, at that case all the three current will come and it will flow through the ground. But in this case, I am not even connecting the neutral point to ground, so my third harmonic current cannot even flow, because all three are in same phase. So the it cannot even flow. It is violating the KCL if it start flowing. So it cannot even flow. So the thing is clear. If my neutral of the star connection is not grounded, my line exciting current or phase current cannot contain the triple harmonic, like third harmonic quantities, or even triple harmonic quantities, third harmonic, ninth harmonic, 15th harmonic, like that. All those harmonics will not be present in if neutral is not grounded. So if my current cannot contain third harmonic, then definitely my the other side, my flux will be flat topped in nature. That's what you also saw. If my exciting current is free from third harmonic quantity, that means my current exciting currents has only fundamental quantities. And if exciting current is fundamental in nature, my flux, the core flux will be flat topped in nature. Flat topped. Core flux will be flat topped in nature. Okay. Now let's um, explain how the flat topped flux will behave. So the flat topped flux look like this, like it will be flat. The same will behave here. So let's say it is for only phase A, phi A of t. Okay, this is my omega t. Okay, and this flux contain fundamental quantity of flux, third harmonic flux, fifth harmonic flux, seventh harmonic flux. Odd quantities, odd harmonic quantities will present, and because of the harmonic present in the flux quantity, my induced voltage will also be will also contain those harmonic quantity, because you can split this phi of t, phi a1 sine omega 1 t, phi a3 sine 3 omega t, like that. So I'm just assuming only up to third harmonic quantity. I'm not even considering the fifth, seventh or all. So because we know the induced EMF can be written as E equals to n d phi by dt. From this formula, you can see the voltage that will get induced across the coil or the per phase. It will also contain harmonic. So n phi a1 omega 1 cos omega 1 t plus uh, 3 phi a3 omega 1 n cos 3 omega 1 t. So the induced voltage will also contain a third harmonic voltage. That is basically not even that is the main cause for the oscillating neutral that we will see. And this is only for phase number. This particular flux I am showing, it is for phase number A, phase A. So it for phase B, phase C, the same kind of flux will be there, but there will be 120-degree displacement in the flux waveforms. Okay. So now if I try to write the flux for all the three phases, phi A of t, phi A1 sine omega 1 t, phi A3 sine 3 omega 1 t. For B phase, phi A1 sine omega 1 t minus 120-degree, phi A3 sine 3 omega 1 t minus 360-degree, phi C of t, phi A1 sine omega 1 t plus 120-degree plus pi a3 sine 3 omega 1 t plus 360-degree, and these all are in same phase. Okay, and this harmonic quantity will give rise to some kind of harmonic induced voltage in the per phase. Now let me also write down the induced voltage equation. Induced voltage phi a1 and maybe va1 sine omega or cos omega 1 t. Let's say it will be derivative of sine, so it will be cos omega 1 t plus va3 cos 3 omega 1 t ev of t v1 v a1 cos 1t plus BA3 cos 3 omega t. Okay, so here coil induced voltage, like transformer coil, let's say these are the A phase, B phase, C phase. So this is your EA1 of t, this is your EB of t, EC of t. So this voltage, the per phase voltage, the coil voltage will also have the harmonical induced voltage, and this is basically this quantities gives rise to the oscillating neutral in case of YY connection if neutral is not grounded. Now we will see the phasor approach, how this is harmful and how it is creating oscillating neutral. But before that, let me explain one more phenomena. Let's say I want to calculate the line voltage. Let's say EAB. I want to calculate. Now, uh, do the calculations. VA1 cos omega 1t, VA3 cos 3 omega 1t minus VA1 cos omega 1t minus 120 degree, VA3 cos 3 omega 1t. These are the same. So my VA1 cos omega 1t minus VA1 cos omega 1t minus 120 degree, and it will be simply root 3 VA1 cos omega 1t plus 30 degree. So this will be my line voltage. So one thing is sure, like line voltage don't even contain the third harmonic component of the voltage. Only phase voltage has the triplet harmonic voltage, triplet harmonic voltages. From the previous slide, we saw the line voltage is free from triple harmonic quantities or third harmonic quantities for in our assumptions. Let's say if we assume only third harmonic quantity in the induced voltage, so line to line voltage will not have any kind of third harmonic voltages. Okay, so if I draw the fundamental quantity, let's say this is my fundamental quantity VA, VV, VC, VA1, VV1, VC1. So these are the per phase voltages due to fundamental induced EMF. Okay, so in this case, my line to line voltage will be, this is my VAB, VAB1, let's say this is my VBC1, this is my VC1, VCA1. Okay, and this was my neutral because of fundamental quantity. Now let's say at t equal to 0, this was my fundamental quantity, and whatever superimposition of the third harmonic will happen, the line voltage will be simply remain same, because we saw from the previous slide, like line voltage will not have any impact because of third harmonic induced voltage. So these are my the fundamental quantity voltage VA1, VB1, VC1, VC1, and plus these are the third harmonic voltages that all are in same phase, let's say VA3. If you superimpose these two voltages, here it will be simply added, here also it will be added, here also it will be added. So it is VA3, VA3 and VA3. All magnitude are same because of third harmonic voltage. So I am representing simply VA3 only. Okay. Now one thing that you can see from this picture, for phase number A, the phasor addition for A phase voltage because of fundamental and third harmonic, simply it is a scalar addition, VA1 plus VA3. So it is a scalar addition. So the magnitude of the overall per phase of the A phase voltage will simply rise. Whereas if you see for B phase, this is my fundamental quantity and this is my third harmonic quantity. The addition here is a vector addition, and vector addition will always give the less magnitude as compared to scalar addition. So the magnitude will be less for the B phase quantity and magnitude will also be less for the C phase quantity, but magnitude will be higher in case of A phase voltage. So there is simply rise in the voltage. So what will the impact? Impact will be if there is any load connected at phase A, let's say phase A is connected, and this voltage VAN1 or let's say VA, this overall voltage will keep on changing. So the load that is that is connected across A phase will also be impacted. At t equal to 0, we saw the A phase voltage is getting increased. And if you try to see the line voltage, let's say this is your line voltage initially, these are the line voltage initially, and this was your neutral. After superimposing your third harmonic voltage, your line voltage the length will be simply length will be same, but there will be shift in the line voltage phasor. So there is a shift in the line voltage. And if I try to see, if this is my VAB line to line voltage, here I have line to line voltage after adding the third harmonic voltage. Magnitude of the VAB is simply same as VAB, but there is shift, because since there is a shift, my neutral point will also shift to some, maybe some end dash point. Okay, so there will be shift. If you try to see at t equal to, let's say, maybe I should say it is a omega t equal to 0. If I say omega t is equal to 30 degree, if it observe at omega t equal to 30 degree, then what will happen? My phasor, my fundamental phasor will rotate by 30 degree, whereas my third harmonic voltage will rotate by 90 degree, because these phasors are rotating at 3 omega speed, whereas the fundamental quantity is rotating at omega speed. So if fundamental quantity is rotating by 30 degree, the third harmonic voltage will rotate by 90 degree. Okay, so let's say this is my reference point, and this is my fundamental quantity, like VA1, VB1, VC1, plus all the third harmonic quantity will simply shift by 90 degree. Okay, and it is 30 degree, and from here they have got shifted by 90 degree because they are rotating thrice of the fundamental quantities. Okay, if you see at this point, you can see the B phase voltage. If, let's say this is your A phase voltage, you are adding third harmonic voltage VA3. Same for the VC3, you're adding, all are in same, so I'm simply representing A3 only. If you want, you can write VB3, VC3, and here again addition VA3. You can see the B phase voltage gets reduced here because of the addition, the vector addition, the or phase vector addition. And here the voltage of the A phase are also not the same, it's changing. So if I try to draw the equivalent line to line voltage, so it will be this one, this one, and this one. See, the line voltage magnitude must be remain same, but my phase voltage is keep on changing. So maybe this time your neutral will shift to some this point in double prime. So my neutral point is keep on changing, and because of that shift, my phase of the because of the change in the neutral point, the phase voltage magnitude will keep on changing, and that will lead to poor performance that is connected across the per phase of the load. Okay, like the load that is connected across phase, the performance will not be good because of the oscillating neutral. Okay, thank you.